students, these are our 5-2 notes, which give us more properties. I think this is our last set of properties or identities for our trig functions. So the first one we're going to look at today is our composite argument properties. Right? The argument is what goes inside of a trig function, right, which is an angle, right? So this argument is an angle. And to compose means to put things together. So our composite argument properties are our properties where the input to a trig function is two angles that are added or subtracted together. So we have really 6 properties here, but we've listed them in 3 lines. The first one says that when we are taking the cosine of 2 angles that are added together, so if I have one angle plus another put inside of the cosine, that's equivalent to taking the cosine of the first angle times the cosine of the second angle. So cosine of A times cosine of B. And if the argument is A plus B, then we're going to subtract the product of the sine of the first angle and the sine of the second. Right? So if we're adding the angles inside the cosine, we will subtract the product of the cosines and the product of the sines. Okay, now, I just want you to understand this notation. If within the cosine we are subtracting 2 angles, so we have the cosine of A minus B, then the identity says that that is equal to the product of the cosines of each of those 2 angles. Right? Now where this is minus, this will be plus the product of the sine of the 2 angles. So that's our composite argument for cosine. For sine, we have that the sine of A plus B, so we're adding our angles inside the sine, will be the sine of the first angle times the cosine of the second. And where we add the angles, we now add as well the cosine of the first times the sine of the second. Right? So for sine, add to add, and then we would subtract to subtract. So if this is minus, this would also be minus. For tangent, we have the tangent of A plus B will equal a fraction, which is the tangent of the first angle plus the tangent of the second angle, all over, right, divided by 1, if this is plus, this is minus, the tangent of A times the tangent of B. If, right, so, why are we not erasing? If we have minus, so if inside the tangent we're subtracting 2 angles, then on top we would subtract the tangent of each, and on the bottom we would add the product to 1. So here's an example of using our composite argument properties. This says use the composite argument property to show that the given equation is an identity. So I have the secant of theta minus 90, and I know this looks like it may be exactly an identity that we proved using our cofunction identities, and I'll quickly walk through that in a minute. But these directions say specifically to use our composite argument properties. So when we look at this, I see the secant, and the argument is the subtraction of 2 angles. So my theta is my A, and my 90 degrees is my B, and we are doing A minus B. Well, if I look up here, I don't have a composite argument property for secant, but I do have a composite argument for cosine. So my first step is I'm going to rewrite this secant as 1 over the cosine of theta minus 90 degrees. So here to here, I used my reciprocal properties. Now, I'm going to replace this cosine of theta minus 90 with its composite argument property. So this is equal to 1 over, right? So this is the cosine of A minus, right, the cosine of B. So that's going to be, according to that property, the cosine of my A, which in this case is theta, times the cosine of my B, which in this case is 90 degrees. And where this is minus, right, this is minus, I'm now going to add, so we will add the sine of my A, which is my first angle theta, times the sine of B, which is the second angle here, which is 90 degrees. Okay, so I went from here to here using my composite argument property. Okay, we can call that a composite angle property as well. So from there, I'm going to go here, right, and I've got to determine what the cosine of 90 and the sine of 90 are. So if I think about my unit circle, right, on that unit circle there is a point at 90 degrees which has coordinates 0, 1. So the cosine of 90 is my x, so that would equal 0. And my sine of 90 is my y, so the sine of 90 equals 1. So if I simplify this, I now have 1 over the cosine of theta times 0. Well, anything times 0 is 0. Plus the sine of theta times 1. Well, anything times 1 doesn't change, so I have sine of theta. Well, that's 1 over sine of theta, right? And what does 1 over sine of theta equal? Well, by our reciprocal identities, that is the cosecant of theta. And we have shown that the cosecant of theta equals the cosecant of theta, and we have proven that identity. Okay, now if I were to do this without my composite argument, right, just a quick review, I could do the secant of theta minus 90 degrees is the same thing as the secant of the opposite of 90 degrees minus theta. And because the secant is an even function, right, so by using my even identity, I know that the secant of the opposite of the angle is the same thing as the secant of the positive of that. So that would be just the positive of 90 minus theta. And we know by our cofunction identities that the secant of 90 minus theta is the same thing as the cosecant of theta. So we've done that proof before, or one like it. It can be, this identity can be proven that way, but again, we were told to use the composite argument, so that would be this way. All right, let's move on. Okay, here we want to show that the cosine of 10 times x times the cosine of 6 times x plus the sine of 10x times the sine of sine x equals the cosine of 4x. Well, let me go back up to my identities here, and I want to point out something. Let me clean this up. Okay, and that is, an identity is a statement that's true, and it can work, right? It can work forwards, which we've just done, or it can work backwards. So what we're looking at in this problem, let's come back down here, looks like the cosine of some angle, let's call that A, times, this should be a cosine, the cosine of some other angle, let's call that B, plus the sine of, right, the same angle I had here, so that's A, times the sine of the same angle that's here, that's B, and this is a plus. So let's go back up and look at these properties. And I have here the cosine of A times the cosine of B plus the sine of A times the sine of B, and that equals the cosine of A minus B. So I can apply that property, right, backwards, and I can, by my composite argument identity, I can rewrite this as the cosine of my A, which is 10x, minus my B, which is 6x. That's supposed to equal the cosine of 4x. Well, right, those are like terms. I've got 10x's minus 6x's, so that's the same thing as the cosine of 4x. And wow, that was easy. We are done. Aren't these identities powerful things, right? Great tools for making a difficult statement simple, which is exactly what we've done. We've simplified that. So this third example, we're going to use the composite argument properties, right? Not giving us an option to transform the left side into a single function of a composite argument. So I'm here looking at the tangent of theta plus the tangent of 27 minus the tangent of theta times the tangent of 27. Well, this could be my A, 27 could be my B, right? So I have the tangent of A plus the tangent of B minus the tangent of A times the tangent of B. So we go back and we look at our tangent properties, right? And we have here that when I have tangent of A plus tangent of B over 1 minus tangent of A times tangent of B, that's the same thing as the tangent of A plus B. So, right, applying right here my composite argument identity, I can rewrite this fraction as the tangent of the A, which is theta, plus the B, which is 27 degrees, and that's supposed to equal 1. Now we're supposed to solve this equation to get our general solution for x or theta, in this case theta. So to get rid of the tangent, we're going to do the arctangent, and we know that the insides, the argument of that tangent, will equal the arctangent of 1, which is the inverse tangent of 1 plus, we're in degrees, so that'll be plus 180 degrees. Solving for theta, we're going to subtract 27, so we get theta equals negative 27 degrees plus my inverse tangent of 1 plus 180 degrees. Well, we know that the tangent is 1 is 45 degrees, or you can put that in your calculator under degree mode, and we get negative 27 degrees plus 45 degrees plus, this is 180 degrees in. Well, 45 minus 27 is 18, so we get 18 degrees plus 180 degrees n, and that is our general solution for theta. So this was our general solution. To find the particular solutions for x, or theta in this case, right, in the domain of 0 to 360, we're just going to take our theta, and 18 falls in that domain, so we'll keep 18. If we add 180 to that, we get 198. And if we added 180 again, that would take us greater than 360, so we get 2 solutions. All right, so we have simplified and we have solved using our composite arguments. Now, our next set of properties are called the double argument properties. So remember, the argument means the same thing as the angle, so these are also referred to as our double angle properties. And double means that we multiply by 2. So your double angle properties are when you've got some angle that is or can be written as 2 times another angle. And those properties are this. We have the sine of 2 times x, we're doubling x, is the same thing as 2 times the sine of just x times the cosine of just x. For the cosine of 2 times some other angle, that's equivalent to the cosine squared of just the angle, not doubled, minus the sine squared, right? And we have 2 others. So this would be the cosine of 2x, can also be expressed as 1 minus 2 sine squared x, and the cosine of 2x can be rewritten as 2 times cosine squared x minus 1. So there is another one for tangent. Let's add that. So we also have the tangent of 2 times x is equal to 2 times the tangent of x over 1 minus the tangent squared of x. So you can add that to your notes. So I'm going to quickly run through the proofs of these, so you can see that this is not just magic, that someone just made this up and thought, oh, wouldn't this be cool? Let's say that this is true, right? But these identities come from other things that we've already seen to be true. So I'm going to take this sine of 2x, right? And doesn't 2 times x mean the same thing as adding two x's together. So the sine of 2x would be the same thing as the sine of x plus x. I'm going to call this first x my a and my second x my b. So this is like having the sine of a plus b. So if I now apply, and I'm going to go from here to here using my composite argument identity for the sine of a plus b, right, that would be the same thing as the sine of a, which is my first x, times the cosine of b, which is my second x, plus the cosine of my a, which is the first x, times the sine of my b, which is the second x. Well, these are like terms, right? Sine times cosine, cosine times sine mean the same thing because multiplication is commutative. So we can add them and we get 2 times the sine of x times the cosine of x, which is our double angle or double argument identity for the sine of 2x. So for cosine of 2x, right, if this is my a, this is my b, then this is the cosine of a plus b, right? Again, using our composite argument identity, that would be the cosine of a, right, which is our first x, times the cosine of our b, which is our second x. Because this is plus, this will be minus, right? The sine of the first angle times the sine of the second angle. Well, that is cosine squared x, right? Cosine times cosine minus sine squared x. And that is our first double angle identity. Now, if we take this and we replace our cosine squared with its Pythagorean identity, right? Cosine squared is the same thing as 1 minus sine squared. And then we subtract sine squared from that. These are like terms, so we can combine them and we get 1 minus 2 sine squared x, which is the second identity for the cosine of 2x. If I take this and now I replace sine squared x with its Pythagorean identity, then I could also get the cosine squared of x minus, sine squared is 1 minus cosine squared of x. We distribute this subtraction and we get cosine squared of x minus 1 plus cosine squared of x. These are like terms. We add those and we get 2 cosine squared of x minus 1, which was our third identity for the cosine of 2x. Right? If we look at the tangent of 2x, here's my a, here's my b, using my composite argument identity, this becomes the tangent of a, right, my first angle, plus the tangent of b, my second angle, over 1 minus the tangent of the first angle, x, times the tangent of the second angle, also x. We simplify that. These are like terms. They're both a tangent of x, so 1 plus another gives me 2 tangent of x over 1 minus, here I'm multiplying 2 of the same thing, so that's tangent squared of x. Right? And we have used our composite argument identities to prove each of those double angle identities. So, right, the value of that comes really in solving equations and simplifying or solving. So I'm looking at here and my job is to solve this equation algebraically. I'm supposed to use the double argument or the half argument. I'm not really showing you the half argument properties, but they come from the double argument. We can use these and not have to learn those. And these are really more important for calculus than the half angle for what we do anyway. So we're going to stick to those double argument. So we want to use those double argument properties in order to transform the equation into a suitable form. A suitable form would be a form that would help me solve for x. And my problem here is that I have x showing up twice and in 2 different functions. If I can get x into one type of function, life is just going to be easier. Well, we have a double angle identity that doesn't say 6 times sine of x times cosine of x, but we have an identity that says 2 times the sine of x times the cosine of x will equal the sine of 2x. So I would have something to use. I could use this if this 6 were a 2? Well, I can make it a 2 because I can do anything I want in an equation as long as I do it to both sides. So if I take both sides and I divide both sides by, not by 2, I want to get a 2. If I divide both sides by 3, then 3 goes into 6 twice, and I have 2 times the sine of x times the cosine of x equals 1/3. Now this looks like this. So I use my double argument identity to replace 2 sine x cosine x with the sine of 2x, which equals 1/3. Now I'm trying to solve for x. It's stuck inside the sine, so what do? We take the arc sine. And when we do, we get 2 possible equations. One is that the inside of the sine, which is 2x, is equal to the arc sine of 1/3, which is the inverse sine of 1/3, plus, let's see, we're in radians, so plus 2 pi n, or right, our second set of solutions come from 2x equals, not 180 because we're in radians, but pi minus the inverse sine of 1/3 plus 2 pi n. We're trying to solve for x, so if we now come in and we multiply through by 1/2, right, same thing as dividing by 2, then I take that 1/2 and I'm going to distribute it to both sides of the equation and to both sides of my addition, and I end up with x equals 1/2 the inverse sine of 1/3 plus pi n, because 1/2 of 2 pi n is just pi n. On the other side, right, this 1/2 goes to the 2x, it goes to the pi, across the subtraction to the inverse sine, and plot across the plus to the 2 pi n. And that leaves me with x equals 1/2 pi minus 1/2 the inverse sine of 1/3 plus 1/2 of 2 pi n, which is pi n. From here I go to my calculator and I evaluate the decimal approximation for 1/2 sine of 1/3. Remember, we're in radians here, so we want our calculator to be in that mode, and we get 0.1699, which would round, by the way, to 0.170, but we would need those 3 decimal places because we've rounded, plus pi n. Here we get x equals, right, what 1/2 pi minus 1/2 the inverse sine of 1/3 is, which is 1.4008, or 1.401 plus pi n. Right? Those are my general solutions. If I'm looking for the particular ones between 0 and 2 pi, remember pi is about 3.14, so 2 pi is about 6.28. So my particular solutions are going to include 0.1699, because that fits in that domain. It's going to include 1.4008. Then if I add pi to this 0.1699, I get 3.3115, be rounded, and if I add pi to this 1.408, I get 4.5424. And those are my particular solutions. Okay, so, right, the easy way, well, I don't know if it's easy, but a way to solve what otherwise would have been a very difficult equation to solve. All right, let's do another one. So this is sine squared of 0.3. Now, don't write this down, just watch this. If I were to take this sine squared of 0.3, which is the sine of theta squared equals 0.3, and I want to solve for theta, so I've got to get rid of the squared. So if I take the square root of both sides, right, then the square root gets rid of the squared, which leaves me the sine of theta. But I have to consider that because this was squared and squaring makes it positive, that what it equals could be positive or negative. So I get plus or minus the square root of 0.3. Well, that gives me two equations, that the sine of theta is a positive square root of 0.3, or that the sine of theta is the negative of the square root of 0.3. Well, for me to now solve for theta, I would have to do the arc sine, which gives me two equations. So I would get theta equals the inverse sine of the square root of 0.3 plus, let's see, we're in degrees, so plus 360 degrees n, or I would get theta equals 180 minus the inverse sine, and so on, right? So this equation would lead me to two equations, and then this one would lead me to another two equations. So I would actually have to solve four equations to find that theta. There's a better way, right? So we're not going to do this. I'm going to take this away. That's more work than what is necessary. So we're going to do this. I have an identity that involves the sine squared of theta, and it says that 1 minus 2 times the sine squared of x is the same thing as the cosine of 2x. So if this here said 1 minus 2 times sine squared of x, I would be in a great place. Well, it doesn't say that. But I'm allowed to do anything I want to an equation to solve it. So watch this, right? This is pretty clever and something you should think about in the future. So if I take this equation and I multiply both sides by a negative 2, remember I'm trying to get 1 minus 2 sine squared of x. Then I get negative 2 times the sine squared of theta equals negative 2 times 0.3, which is negative 0.6. Okay? So now I've got this negative 2. I would like to have a 1. So if it's negative 2. If I add 1 to both sides of this equation, then this is equivalent to having 1 minus 2 sine squared of theta equals negative 0.6 plus 1, which is positive 0.4. Well, now, what does 1 minus 2 sine squared of theta equal? Well, it's the same thing as the cosine of 2 times my angle. So I can replace that with the cosine of 2 theta using my double argument identity. So I have the cosine of 2 theta equals 0.4, right? That's inside my cosine. I'm trying to find theta, so I take the arc cosine of both sides, and I get 2 theta equals arc cosine is plus or minus inverse cosine of 0.4 plus, let's see, we're in degrees, so plus 360 degrees, and I want to get the theta by itself, so I'm going to divide both sides by 1/2, and I get theta equals, that multiplication goes across that plus or minus, so plus or minus 1/2 times the inverse cosine of 0.4 plus, this 1/2 goes across this plus sign, and half of 360 is 180 degrees n. This is my general solution for theta. For me to find the particular solutions that fall between 0 and 360, I would get theta let me do this. Let's change that to a decimal so we can see how big that is. So plus or minus what 1/2 times the inverse cosine of 0.4 is, which is about 33.211 degrees, plus my 180 degrees n. So that's my general as well, right? Also my general. And for my particular solutions, I would get theta equals negative 33.211 does not fall in this domain, but positive does. So I got 33.211 degrees. And then if I take the negative and add 180 to it, that gives me 146.789 degrees. I take this 33.211, add 180 to that, and I get 213.211 degrees. add 180 to the 146, and that gives me 326.789 degrees. Okay, so that started with a pretty clever change to get this in the place where I could use my double angle. The value of that is it got me to one function that contained my variable, right, that wasn't squared. So that was a great thing. All right. 2 more examples and we're done. I know this is a lot, right, but be patient. Not very many videos in this unit. So here I have the tangent of 1 minus, I'm trying to prove that the tangent of beta is equal to 1 minus the cosine of 2 times beta. So what I want you to recognize is that inside this cosine and sine, we have 2 times an angle, and inside this tangent, we just have 1 times that angle. So as usual, we're going to start with the more complicated side, and we're going to work with that, and we're trying to get that to be equivalent to the tangent of beta. Okay, well, I know something about the cosine of 2 times an angle. Okay, and I know that that can equal 3 different things. Well, my tangent is my sine over my cosine. So I would sure like this function to be in terms of sine instead of cosine. Well, I know one of the definitions for the cosine of 2 times x is 1 minus 2 times the cosine squared of just x. No, I'm sorry, 1 minus 2 times the sine squared of 2x. So if I make that substitution, then I have my 1 minus, replacing cosine of 2x with 1 minus 2 times the sine squared of 2 beta, it would be. Then that's going to give me, oh, good things on top. Now on the bottom I have a sine, tangent sine over cosine, so I would love to get a cosine out of the sine of 2 beta. Well, I know that the sine of 2x is the same thing as 2 times the sine of x times the cosine of x, right? So here are my identities. So if I replace the sine of 2 beta with its double angle identity, which would be 2 times the sine of beta times the cosine of beta, then that gives me a cosine on the bottom, which I wanted, but I've got this sine. Let's see what happens. If we distribute this negative, right, across my subtraction, I get 1 minus 1 plus 2 times sine squared of 2 beta over 2 times the sine of beta cosine of beta. Well, 1 minus 1 is 0, so I have 2 times sine squared of, oh, this was not 2 beta, this is just beta. Ah, this was just x, my apologies. Beta, okay. 2 times the sine squared of beta over 2 times the sine of beta cosine of beta. Well, my 2's divide out, one of the sines divide out, and so what I'm left with, right, we're trying to have tangent of beta, is I'm left with a sine of beta over a cosine of beta. Well, by our quotient identity, that is exactly what we're looking for, and we have proven that identity. All right, one more, and that's that the cosine squared of 3x equals 1/2 of 1 plus the cosine of 6x. So what I want you to notice is we've got cosine of both sides. On this side I have 6x, on this side I have 3x. And isn't this argument twice what this is? Okay. So your answer of course should be yes, Mrs. Key, it is. So if I rewrite this, this is 1/2 of 1 plus the cosine of 6x, which is 2 times 3x. If I think of this 3x as my a, then this is equivalent to the cosine of 2 times an angle, right? Which is, again, we've got 3 identities for the cosine of 2 times an angle, but I'm looking to end up with a cosine squared. So that cosine of 2 times an angle is the same thing as 2 times the cosine squared of the single version of that angle minus 1. Well, my angle is actually 3x, so that would be, if I called this A, right, that would be my A. So if I come here and I've got 1/2 times 1 plus the cosine of 2 times A is the same thing as 2 times the cosine squared of my A, which in this case is 3x, minus 1. Simplifying that, I get 1/2 is equal to, well, 1 minus 1 is 0, so that's 2 times cosine squared of 3x. 1/2 times 2 is just 1, so that is the cosine squared of 3x, which is exactly where we wanted to be. Okay, so this is called an angle reducing process. We had 6x, we wanted to reduce it to half. Right, so we recognized that we could use that double angle identity. Okay, so there's a lot to this, but once again, you guys are so bright and so capable. I know that you're going to get this. You're going to do a great job. So that's it. Long one, I know, but it's going to be worth it. Thank you for your attention.